Imagine a brand new AI screening system designed to detect a rare, deadly virus. The developers proudly announce it has a 99% accuracy rate. On paper, it sounds perfect, but there's a catch. The virus only infects 1 out of every 100 people. If the algorithm is programmed to simply output the word healthy for every single patient it sees, it will be correct 99 times out of 100. Out of 100 data points, 99 belong to the majority class, and only 1 is an outlier. The system sweeps all of them into a single healthy bucket, hitting a 99% success rate, but failing to isolate the threat. This is the trap of an imbalanced dataset. In the real world, relying on a flat accuracy percentage under these conditions is dangerous. A model that misses every actual anomaly is technically accurate, but operationally useless. To find out if a system actually works, we have to look past the superficial score. We must run the algorithm through a separated testing gauntlet, using metrics that account for the specific rarity of the event we're trying to find. Building that gauntlet starts by splitting our data into strict categories. The first is the training data. This phase is like a student pilot racking up hours in a turbulent flight simulator. The algorithm makes mistakes, learns, and adjusts its internal logic. But you wouldn't give a pilot a license just because they mastered a simulation. If you test a model using the exact same data it trained on, you run the risk of overfitting. The model might just be memorizing the answers to that specific test, rather than learning the underlying rules. So we introduce a second batch, the validation data. This acts like an instructor sitting next to the pilot, tweaking the simulator's weather conditions and mechanical failures to fine-tune the model's performance, without giving away the final exam. Finally, we have the test data. This is an entirely untouched, independent dataset. It serves as the final road test, simulating what the model will face in reality. If even a single piece of that final test data accidentally slips into the training phase, a problem known as data leakage, the entire evaluation is invalidated. Enforcing these barriers ensures the model is learning generalizable patterns, rather than just memorizing noise, providing a statistical baseline for how it might perform on unseen data. Once the model takes that final exam, we grade it using a scorecard called a confusion matrix. This grid breaks down exactly how a classification model makes its mistakes. Looking at the diagonal, we find our successful hits. True positives are the threats it correctly identified. True negatives are the safe items it correctly ignored. The errors occur in the other corners. A false positive is a false alarm, flagging a healthy patient as sick. By comparing our true positives against those false alarms, we calculate a metric called precision. High precision means that when the alarm rings, it's almost certainly a real threat. You optimize for precision when a false alarm carries a high financial or operational cost. On the other hand, a false negative is a missed detection. This is when the model looks at a sick patient and calls them healthy. Comparing true positives against these missed detections gives us recall. High recall means the model catches almost every threat that exists. You prioritize recall when missing a detection could be deadly. Because pushing precision up often drives recall down, we use the F1 score to strike a mathematical balance between the two, providing a single number to evaluate overall performance. We can also visualize this diagnostic sorting ability using an ROC curve. This chart plots the detection rate against the false alarm rate across all possible thresholds. A curve bowing sharply toward the top left means the model excels at distinguishing between classes, while a flat diagonal line represents random guessing. By dissecting every prediction into these distinct quadrants, we eliminate the blind spots created by relying on a single accuracy score. A model scoring well on a single test dataset isn't enough. It might have just gotten a lucky batch of questions. To rule out statistical luck, we use k-fold cross-validation. This diagram shows a dataset sliced into 5 equal blocks, where one specific segment is reserved as the final test, and the rest act as training data. We repeat the entire training process 5 times, rotating the test block each cycle. If the model scores well on every fold, we have evidence that its performance is consistent and stable. So far, we've evaluated classification models, algorithms that sort data into discrete boxes. A regression model, however, predicts continuous numbers, like tomorrow's stock price. You can't grade a continuous number as simply right or wrong. Instead, regression requires metrics like mean absolute error to measure the exact physical distance between the model's prediction and the actual value. Rigorous evaluation requires selecting a mathematical scorecard that matches the specific architecture and objective of the algorithm you built. Passing the initial tests does not guarantee success. When live, real-world data diverges from historical training data, the model experiences a distribution shift. It operates like a vehicle built for a smooth test track that suddenly finds itself in a chaotic off-road environment. To survive deployment, developers must evaluate models for subgroup fairness and robustness. The algorithm has to perform reliably across different demographics and edge cases, rather than just hitting a high average score for the majority. And when a model inevitably makes a mistake, choosing whether to prioritize precision or recall is a human decision, weighed against the specific ethical and financial costs of a false alarm versus a misdetection. An algorithm is never truly finished. Once it goes live, it requires continuous post-deployment monitoring to catch performance degradation over time. Safe AI requires strict data boundaries, context-aware scorecards, and constant human accountability.
If you enjoyed this video, please like, comment, and subscribe for more AI and technology content. Thanks for watching.